All right, so this is lecture 12, and today is the 28th of April 2021. So where are we? We were talking about force vibration of under harmonic systems. So this is where we are as far as the course goes. We
Professor,
studied.
could you focus your screen a little bit more?
Oh, sure. I'm glad you said that. Otherwise, I would not have noticed it. Here we go. That's better, right? Okay, so we're talking about force vibration under harmonic load. So we studied the undamped systems, and now we're going to discuss the force vibration of damped systems. So in this case, this was the equation of motion, okay, where F naught is the amplitude of the forcing function. Of course, you could write the equation also in this form, the alternative form. For the damped system, what is the equation of motion? You have mu double dot plus cu dot plus ku is equal to F naught sine omega t. So now we have a system which is damped and subjected to a harmonic forcing function. So basically, we want to again solve this differential equation. Uh, and of course, if you want, you can write that in this form also, which is the alternative form. Okay, omega n squared u is equal to F naught over m sine omega t. So again, you remember the total solution would be the sum of the homogeneous and the particular or the steady state solution. And in order to find the steady state solution, we assume that it is, if you remember from differential equation, we assume that the solution is of this form. It is harmonic, but it has also a phase angle. So there are two unknowns that we want to find in order to uh, basically come up with an expression for the steady state response. Okay, so what do you do? Like before, you would just simply substitute this assumed solution into the equation of motion. So if you do that, let's see, this is what I'm going to do. That is, you take this second derivative and first derivative, okay, of this and substitute it into this equation and put the two sides equal, right? So if you do that, you will see that you end up with an expression like this. After you simplify that, factor out all the uh, terms and common terms and so on, you end up with something like this: omega n squared minus omega squared times sine omega t minus theta plus 2 zeta omega n omega cosine omega t minus theta. Okay, that's what you will end up with, f0 naught over m sine omega t. So after you do the substitution and simplification and all of that, okay, this is what you end up with, okay? So what I will do, how do I solve this problem? How do I find A from here and theta, which are the unknowns? I would expand these using trig identity. Okay. Sine of alpha minus beta is sine alpha, cosine beta plus cosine beta sine alpha. And same thing with this is sine, sine, cosine, cosine. So if you use the trig identity and rearrange the terms, you end up with basically only sine omega t and cosine theta and so on. These are the two equations that you end up with. You end up with A times uh, uh, omega n squared minus omega squared, okay, cosine theta plus 2 zeta omega n omega sine theta times sine omega t plus a times omega n squared minus omega squared sine theta minus 2 zeta omega n cosine theta is equal to f naught over m sine omega t. So this is the algebraic equation that you need to use to find a and theta. Okay, how do you do that? Well, on the left-hand side, you do have what? Let me admit him. Okay. On the left-hand side, you have this times sine omega t, and then you have a term like this. You need to put the coefficient of sine omega t on the left-hand side equal to the coefficient of omega t on the right-hand side. So this is what you have. Omega n squared minus omega squared cosine omega plus 2 zeta omega n sine theta. This is f0 over m. And the other one is a constant. On the other side, you don't have a constant, or the constant value is 0. So this would be then equal to 0. Okay? Sine theta minus 2 zeta omega n cosine theta is equal to 0. So you have two equations and two unknowns that you can solve for A and theta. I don't want to go further into the algebra of it. In fact, in the other class, I didn't even go this far, but you can see how you can solve this problem. This is simultaneous equations, right? If you add these up, these two terms cancel out. And the right-hand side would be simply f0 over m. So the left-hand side, let me just do one of them. So at least to show you how you can come up with theta. If I want to find theta, okay, I add these two. So this and that cancel out. So you end up basically with a times omega n squared minus omega squared, okay, times cosine theta, okay, plus a omega n squared minus omega squared sine theta is equal to f0 over m. So you need to divide this both sides by cosine theta. So you end up with this times tangent theta. The other side you have 1 over cosine theta. 1 over cosine theta is the square root of 1 over 1 minus tangent square. So you use trig identities and so on. I don't get through that. Because when once you do that, then you want cosine theta, substitute it in here. You go through all kinds of algebra, and eventually the solution would be the tangent of theta comes out to be this function, okay? And A will be this value, F0 over K, 1 minus R squared plus 4 zeta squared R square root of that. Okay, so these are the two unknowns that you will be able to find. What's the importance? So what is the big deal about this? Let's look at the amplitude and of course for the phase angle.
Sorry, Professor,
Okay,
real quick, could you show that last formula again for just a second?
sure. I'm gonna rewrite this several times as you
Okay,
will see.
thank you.
Right. So uh, in the case of, okay, in the case of undamped system, okay, the amplitude was, which we call that magnification factor, was just simply this, okay, which obviously you can see if the damping is 0, that's what you come up with. But now, when damping is not 0, what you see is this magnification factor, which is that amplitude, is this, right? So now let's take a close look here, okay? Let's take a close look at this. In the case of undamped systems, we plotted this function, and this is how it looked like, right? Damping was 0. This function goes to infinity at r equal to 1. If at r is equal to a square root of 2, comes down and goes to 0 at when the frequency ratio goes to infinity. Okay, so this was the frequency response function or the magnification factor for the case of undamped systems. And of course, the conclusion we reached was, remember, when r is greater than the square root of 2, what this curve told you was that compared with the static displacement, remember that example of that beam? If you have a static load of this magnitude and it experiences a displacement of delta, what happens if this becomes a cyclic load, a sinusoidal load with that amplitude, the corresponding static displacement is determined by simply what? By this HR that is multiplied by that corresponding static displacement. And from this observation, we saw that if the frequency ratio is greater than the square root of 2, that dynamic displacement is always less than the corresponding static displacement. So that's the only observation we made in this case. And also when r is equal to 1, the displacement is unbounded, goes to infinity, or you had resonance. Now, what happens now in this case when, as we said, the amplitude is f0 over k times this function, h of r, which is no longer a function of only r, but also a function of zeta. where this function is this 1 minus r squared plus 4 zeta squared r squared. And the phase value, which in the case of undamped was only 0 or 180 degrees, now is determined from this equation, 2 zeta r over 1 minus r squared. So we're going to spend some time and focus on this curve and understand the significance of this frequency response function in the case of damped systems, okay? If you plot this frequency response function, okay? If you plot that function for different values of R and zeta, you will see something like this. If this is 1, so this is R equal to 1. So in the background, I will put the case of undamped system here, okay? If you plot this function, H of R and zeta, you see that for some value of, let's say, zeta, you have something like this. As zeta increases, okay, the peak value of this curve shifts. This is the peak value, maximum value of this H function shifts to the left, further and further to the left of R equal to 1. So versus this is zeta 0.1, this is, let's say, zeta 0.2, let's say zeta 0.5. As you increase zeta and it exceeds damping ratio of 0.71, all these curves now fall below this threshold of that corresponds to the static displacement. So we're going to focus on this and really interpret the behavior of this frequency response function in more details, because understanding of this frequency response function is very important. And later on, especially when we get into multi-degree of freedom systems, it is very significant. So let's first make some simple observation. Simple observation number 1 is when the damping ratio is 0, this frequency response function reduces to 1 over 1 minus r squared, which is for undamped systems. So, in other words, this function that we derive is the general case of the frequency response function from which you can obtain the frequency response function for the undamped system, because you can easily see that 1 minus r squared plus 4 zeta squared r squared. When zeta is equal to 0, this term cancels out, so the square root comes out, so this becomes 1 over 1 minus r squared. Observation number 2, you will see, and we will prove that as zeta increases, okay, you see that amplitude will decrease because the maximum value of this frequency response function decreases. In other words, this is decreasing, so the amplitude of the response was f0 over k times this h. So the amplitude of the response, which is this, would decrease. you also notice that the peak value, okay, shifts to the left of R equal to 1. That means as damping increases in the system, the maximum value will be reached at a frequency which is less and less than, increasingly less than the natural frequency. Remember, in the undamped case, maximum value, which is of course unbounded, occurs at R equal to 1, which is the case of resonance. In the case of the damped systems, the maximum value occurs at a point when R is actually less than 1, or the frequency of the forcing function is less than natural frequency. And depending on what the damping ratio is, as you increase the damping ratio, this maximum value occurs before, increasingly further and further before natural frequency. And the third observation that, as I told you, is that as the damping ratio becomes greater than 0.71, and we'll prove that, then no matter what, okay, the displacement or the maximum displacement is always less than the corresponding static displacement. When damping ratio is more than 70%, it's impossible that the system will ever reach the corresponding static displacement. So let's, I just told you these, but let's prove why these behaviors happen, okay? So in
Professor,
order, yes.
so do you think you could reiterate that point C, like what happens if that's greater than 0.71 one more time?
Yeah. You
Of
know, you
understanding
see
that
that
part.
if the zeta is greater than 0.7, these curves always fall below this line. That means the amplification factor, which is this function, is always less than 1.
Mhm.
So the maximum displacement of the system under harmonic load is this H times F0 over K, which is
Mhm.
the corresponding static displacement. So when the damping is greater than 0.7, I mean 0.7 or 70%, the dynamic displacement is always less than the corresponding static displacement. Okay,
Thanks.
that's what. Now let's see why and why it is so. So we are going to study this closely. This is the frequency response function. Okay, so let me write that down again. So let's go back to basically to first claim that I made, that as damping increases, you see the shift of the peak toward the left of R equal to 1. And then I claim that if damping goes beyond 0.71, this H value is always less than 1. So let's prove those. How do you prove those? In order to find the maximum value of this, right? So in order to find the peak value of H, how do you do that? You need to take the derivative of this with respect to the variable R, because we want to show that what happens as damping increases, right? So we will keep that in mind. So we need to take the derivative with respect to R, equate that to 0. So you find the R value, for which H is maximum, right? So let's do that. Take the derivative with respect to R. If, in other words, this is an algebraic expression, you know that the first derivative is derivative of numerator times denominator minus denominator times numerator divided by this, square root of that and so on. So I don't get to that. So you go back to your algebra, calculus, you see that the derivative of this function would be derived to be 1 minus r squared minus 2 zeta squared divided by 1 minus r squared plus 4 zeta squared r squared 3/2. So that is simplified to be this expression. So I need to equate this to 0 in order to find the R values for which this function is maximum, right? So when you say you need to set this equal to 0, means that you set the numerator equal to 0. So what happens? There are two possibilities. When you set that equal to 0, either R is equal to 0 or this is equal to 0. So there are two possibilities, right? So let's look at this. What does R equal to 0 means? Means you're here, okay? When R is equal to 0, okay, what happens? H is equal to 1. So that means this system is not even moving, right? Because frequency of the forcing function is 0. So corresponds to this value, which we know that the maximum displacement of a system subjected to a force of F naught is this. The amplification is 1, right? But this is the case that is more interesting. Let's look at this. So this is a function of two variables, right? So if I want to find out at what corresponding value of R I have maximum, at what value of zeta I have the maximum value or a minimum value, what do I do? In other words, how do I know that the R value I find from here correspond to a maximum value or minimum value? Well, how do you do that? You take a second derivative, right? In other words, you take the derivative of this derivative, okay? And if this value is positive, corresponds to minimum. If it is negative, corresponds to maximum. So let's take the derivative of this with respect to R. The second order derivative of H would be 1 minus 2 zeta squared, right? Take the derivative of this with, with respect to R, and you will see that you get this, right? So now, when would this be positive? It will be positive if 2 zeta squared is less than 1, or zeta is less than, if you take the zeta squared is less than 1/2, just take the square root, you see that is this. It is going to be minimum when this 2 zeta squared, okay, is greater than 1. That would be negative, right? That means zeta is greater than 0.71. So it is for that reason now you can see that, as I said, the maximum values will only occur when you have a damping ratio that is less than 0.71. You have all these peaks, okay? The minimum value, which is when this falls below this, okay, would only happen when zeta is greater than 0.71. So we demonstrated that why this thing happens, that why for, now, let's pay attention even further. So what we are saying is that, okay, is if you, for all these curves, okay, the maximum value, and let me also do the benchmark here for the undamped, which is 2, this is 1. So for all these curves, maximum value happens when zeta, for all of these, zeta is less than 0.71. And you get to the minimum value, okay, when zeta is greater than 0.71. Okay. Now, if you had the derivative, right? The first order derivative, which was this equal to 0. Okay. So if you want to find now the maximum value, what is this maximum value? Okay. We said that in order to find the actual maximum value for the case that zeta is less than 0.71, we want to see, okay, what is this maximum value? So for the case of less than zeta 0.71, where we know the maximum values occur, right? We want to find that maximum value. So you need to find R from here, substitute it into the equation for H to find the corresponding value, right, for the maximum. So R is square root of, from here, okay, if you set this equal to 0 to find R is 1 minus 2 zeta squared, right? You see that, first of all, zeta is less than 0.71, okay? So you can easily see that when zeta is less than 0.71, okay, let's play with some numbers. If zeta, let's say, is 0.1, okay, R value is going to be greater than R for 0.3. Just substitute in here. If you put 0.1 or 0.3, what that means, that means the maximum value occurs at a point that is closer to R equal to 1. But as the damping ratio increases, the R value will decrease. So you can see that as damping ratio increases, R value will decrease within this range, of course. You remember when I first claimed as the damping ratio increases, the shift of the peak value is further and further away from R equal to 1. So this is one observation that we make. Also, another interesting observation is this. Given that this is maximum value is 0.71, so R is all, of course, is positive. This um, 1 minus 2 zeta squared is greater than 0. So 1 minus 2 zeta, 1 is less than 2 zeta squared 1. So zeta is less than 0.71. So even from here, you can see that what we claim is true. That is, for this peak value occurs, zeta is less than 0.71. But now, let's substitute this value into h, which is that function. I'm not going to, I will rewrite that. So this is the function 1 minus r squared plus 4 zeta squared r squared. Let's substitute this into this function to find h max. H max meaning, for instance, for a particular value of zeta, this is the peak value. If you do that, substitute that in this, you find that maximum value would be 1 over 2 zeta, 1 minus zeta squared, okay? Given that zeta is less than 0.7, zeta squared is a small number. So we can say that approximately this whole thing is almost equal to 1 because this is negligible. So H max is almost equal to 1 over 2 zeta, okay? In practice, we assign a name to this quantity. First of all, let's look at from the graph what that means, okay? What we are saying is that if, let's say, you have a system, you plot its frequency response function, okay? This is the peak value that you found, okay? This is that peak value, okay? This is H max, which is almost 1 over 2 zeta, okay? What this is going to tell you, we just introduced a way to evaluate the damping ratio, a different way to find the damping ratio in the system, which is actually an easier way. You remember we introduced one way of finding the damping ratio of the system using logarithmic decrement by using the time response of a damped system. If you plot the time response, you see that it is not that easy to measure these two consecutive amplitude and use a logarithmic decrement. Whereas by plotting a frequency response function, you have a nice and clean curve, relatively speaking, because you always have noise, but it's easy to measure the peak value of this curve, and then you can quickly find the damping ratio, because the damping ratio is what? Is 2 times that H max, right? In other words, from here, you find, I'm sorry, damping ratio from here is what? 1 over 2H, right? 2H max. In practice, we call this maximum value Q. You see that as the damping ratio increases, right, this Q will decrease. If the damping ratio decreases, Q will increase. So for that reason, we use a terminology. A low Q system means that high damping or highly damped. A high Q system means low damping. And of course, we prefer, depending on the situation, either high Q system or a low Q system. Okay, and you can see it is obvious, right? Because if you plot, the higher the value of the damping is, this is going to drop, right? So that means, basically you have a lower maximum value, okay, which corresponds to the determination of the damping ratio in the system. So with that said, let me just summarize what we have done and get prepared for the next topic. Harmonic excitation of damped system is the most important topic covered in the introductory course. So we're going to be spending quite a bit of time on that. And understanding of the frequency response function is one of the things that is important and is really a foundation for a number of concepts that we will introduce later. So let me just summarize what we did today. We introduced the frequency response function for the case of damped system, which is this function. This frequency response function represents, okay, magnification of corresponding static response. This is the first thing we learn. In other words, static response under F naught, dynamic response under the cyclic load. Second point or observation is for all systems. So maybe I should have called this summary or observations. Okay. For all systems with a damping ratio of less than 70%, roughly speaking, maximum H, okay, occurs at R is equal to 1 minus 2 zeta squared. And by using Q, which is the maximum value of this H function, which is approximately 1 over 2 zeta, we can find damping ratio in the system by just plotting the frequency response function. For cases that zeta is greater than 70%, H max is always less than 1, or the dynamic displacement is always less than the corresponding static displacement. Last observation is this. We said that in the case of undamped system, we saw that when we have two ways, we said that the maximum value of the dynamic displacement occurs when R is greater than the square root of 2. Okay, it's always less. The maximum value is always less than the static displacement when the R value is greater than 2. In the case of damped systems, we see that there are two ways to reduce the maximum value. One possibility is by increasing the damping ratio. As you increase the damping ratio, you reduce the amplitude of the dynamic response. Of course, there's a limit to that, because if you increase it to the point that this goes to 0.71, you definitely guaranteed, but this may not be a good idea because it may result into too much energy dissipation or heat or whatnot. But we see that in the case of even damped system, we can also say the same thing, that when the frequency is greater than square root of 1, we are guaranteed that the dynamic displacement is less than the corresponding static displacement. So this frequency ratio has a significance, okay? So bear these in mind. Next time, we're going to continue the discussion of the harmonic excitation of damped system and introduce some more interesting topics that have very important practical applications, starting with rotating on balance. Then we get to transmissibility ratio, vibration isolation. All of these are topics that we will see are very interesting, very practical or important practical applications, and they're all based on these concepts that we introduced in assessment or analysis of the response of an undamped system subjected to harmonic excitation. So with that said, I'm just going to stop here and answer any questions.